When an X-ray beam hits a protein crystal, we don't get a simple photograph of a molecule. We get a physical scattering event, capturing only the discrete diffraction spots cast into reciprocal space. The central problem of structural biology is working backward from this scattered pattern. We have to mathematically invert the physical diffraction process to reconstruct the continuous three-dimensional electron density of the original molecule. The engine driving this inversion is the Fourier transform. Instead of a continuous integral, we rely on a discrete mathematical summation to pull spatial information out of the scattered wave data. This transformation is strictly bijective. Information in the real spatial domain maps directly to the reciprocal frequency domain, and vice versa. To execute this math, every reciprocal index vector, HKL, requires two measured parameters, the structure factor amplitude and its corresponding phase angle. But a physical X-ray detector only measures intensity. It records the scalar amplitudes, but the physical detection of the scattered photons entirely destroys the phase information. Because the hardware fails to capture them, the missing phases must be generated separately, relying on dedicated experimental phasing techniques or molecular replacement. The final electron density map is a summation of these two distinct inputs, measured amplitudes and computed phases. Consequently, an error in either parameter predictably warps the resulting three-dimensional mesh. A structural map is not an image captured by a lens, it is a highly sensitive mathematical reconstruction. Every limitation of the physical crystal and the detector forces a specific geometric artifact into the real space domain. To reconstruct electron density, we use a discrete Fourier summation, combining structural amplitude, phase, and fractional coordinate terms. Because reciprocal space is centrosymmetric, imaginary sine terms cancel out, leaving a real cosine summation. This explains how complex structure factors yield a purely real physical observable. We can test how this summation behaves physically using a simple one-dimensional model. Let's place a 6-electron carbon atom and an 8-electron oxygen atom at specific fractional coordinates. At low resolution, 4 angstrom data, we get this broad red distribution, lacking the high-frequency waves to construct a sharp peak. Feeding 3 and 2 angstrom data, the peaks rise and tighten. At 1 angstrom, they converge sharply, correctly reflecting the carbon and oxygen electron counts. If a structure cannot scatter X-rays at high diffraction angles, missing Fourier terms physically cap the sharpness of an atom's position. This cap on spatial precision, the inability to perfectly isolate an atom in space, is the strict mathematical definition of a crystallographic resolution limit. Translating these continuous functions into digital maps requires applying the Nyquist theorem. To preserve structural information, the Fourier grid spacing must be at least half the minimum d-spacing. Resolution is not an image focus issue, it is a hard mathematical boundary that dictates the exact precision with which we can isolate an atom in space. Even with high-resolution data, atoms are rarely static. We account for an atom's mean displacement from its equilibrium position using a b-factor. This chart shows the effect. Increasing the b-factor attenuates the atomic scattering factor in reciprocal space, following a smooth Gaussian decay curve. According to the Fourier convolution theorem, a Gaussian decay in reciprocal space corresponds precisely to a Gaussian point spread convolution in real space. On a three-dimensional protein structure, this convolution visibly blurs the atomic mesh, spreading the defined volume outward. Because b-factors spread the electron density, a fully occupied atom with high thermal motion produces an overall signal attenuation strikingly similar to an atom that is rigidly fixed but only partially present. We can see this ambiguity by comparing the Fourier peaks for an oxygen atom and a heavier magnesium ion. Look closely at the magnesium peak on the right. The blue line shows partial occupancy with a normal b-factor, while the red line represents full occupancy with a high b-factor. In the sterile environment of a 1D model, the peak shapes differ slightly, but in a noisy 3D protein map, these two scenarios generate essentially identical signals. Separating dynamic motion from physical absence requires data outside the math. Structural biologists must apply chemical constraints, like expected bond distances and coordination geometry, to differentiate a shaking atom from a missing one. The mathematical reconstruction process is entirely blind to chemistry. The map alone cannot distinguish thermal vibration from a vacancy in the lattice. A smooth Gaussian decay limits resolution naturally, but actively cutting off data creates an entirely different class of map artifacts. Truncating reciprocal data at a point where significant signal still exists is mathematically equivalent to multiplying the data by a sharp Heaviside step function, instantly dropping to zero. When transformed into real space, this sharp cutoff convolves the true density with a sin x over x function. The result is visible here on the red line. Oscillatory truncation ripples radiate outward from the peak center. In a real map, these ripples create artificial holes that obscure neighboring structural features. Systematic truncation damages the map severely, but the Fourier transform handles random data loss, like reflections discarded due to ice rings, much better. As long as the distribution of missing data is random, the summation remains robust. Even moving from 20% missing data to 50%, the core peptide trace is fully intact, though the overall noise increases. The true danger lies in systematically absent data. This occurs when a complete rotation range isn't covered, or if the crystal dies prematurely. Omitting a continuous wedge of reciprocal space leaves an unbalanced hole in the Fourier summation. This translates directly into real space, generating severe, directional streaks perpendicular to the missing zone. In beta sheets, these artificial streaks bridge the strands, making accurate modeling nearly impossible. Map artifacts are not random noise. Truncation ripples and directional streaks are precise geometric signatures that diagnose exactly how the physical data collection was compromised. Because a three-dimensional reconstruction is simply a grid of numerical density values, crystallographers must visually threshold this data using continuous contour lines to build a usable model. The universal metric for this threshold is the standard deviation, or sigma, evaluated above the mean electron density of the entire map. At a high 5 sigma contour, the map isolates intense peaks like tightly bound atoms. Lowering to 1 sigma reveals the continuous molecular envelope needed to trace the backbone. Dropping to 0.5 sigma is dangerous. Noise mimics structure, tempting researchers to model non-existent features. Every map is governed by these same physical constraints. Resolution determines the ultimate sharpness. B factors dictate the physical spread. Missing data dictates geometric distortion. A rigorous structural biologist doesn't merely look at an electron density map. Instead, they read it, decoding the reciprocal space constraints written directly into the geometry of the real space reconstruction.